I still want to emphasize, I hate to do that, but I want to emphasize that in the quiz, please do it honestly. Okay. I really, you know, you guys are almost graduating, junior, right? Senior going to next year. So you don't need me to repeat these things. But I do find a couple of you have exactly identical wrong answers. Okay. You know, you see how many we got 10 out of 10 for this quiz? Maybe 2, right? But most of you have something wrong in it, right? Have a little mistakes in there. But if you share your answer with others, copy each other's without understanding it, it's very likely you get 2 identical wrong answer sheets. Okay, so it's very, very easy for me to identify who's cheating. Okay, so this is the second time I mentioned this. So I deducted some points, but modestly. Okay, not much. Okay, but I did deduct some points. So I don't care who's copying who. Okay, so both of you, if you copy each other, it's equivalent. Okay, so please don't do that. Only 3 classes left. We have 2-3 quizzes left. Don't, you know, at the end of the semester, due to those stupidity and significantly affect your grade. Okay, don't do that. Not worth it. Okay, you see your project, everything's good, right? It's not not too bad, right? So don't risk it by doing the stupid things. Okay, so okay, now let's yes.
On that quiz, the last part was to find the power.
Yeah.
I guess you had said how to find the power. I must have not written it down. How do we find the power once we have the force?
Yeah. The goal of those quiz is make sure you're 100% listening to what I say. Okay, write down the notes appropriately. Okay, so force times the velocity, that's the power. Okay. Did you write it down now? Now you know it, right? So the flow speed times the resistance force you need to overcome. That's the power you need. Okay. So now turbulent pipe flow. Okay, that's important because most of the applications, you know, in practical work you do, you're dealing with turbulent pipe flows. Okay, let me share my screen now. Where's my whiteboard? Is my whiteboard is not on. Okay, hold on. Let me turn on my whiteboard first. Okay, let me look at, do I have a, okay, that's the one we can continue. Okay. Let me start sharing. Okay, you can see it, right?
Yes, sir.
Okay, good. Now, turbulent pipe, do you remember in the turbulent boundary layer? Okay, we don't have an analytical solution for that, right? We use the Reynolds analogy, right? Reynolds analogy to relate the shear, okay, relate the friction, okay, to the heat transfer, okay. So equation 5.114a, that's the Reynolds analogy for the pipe flow. Okay, so everything starts from there. Okay, not everything, but some of the equations start from there, right? I'm presenting to some. You have many different choices for turbulent pipe flow. Okay, so this is the Reynolds analogy for the pipe. So it looks different comparing to the boundary layer, right? Surface plate, of course, it's different. Okay, the relation is a little bit different. So your Reynolds, your Nusselt number is in the Stanton number, right? So F is the friction coefficient. So you can get it from the what we talked about previously. So if you rearrange this equation, you take the Nusselt number out of the Stanton number, it becomes Nusselt number equals 0.0395 times Reynolds number 3/4, I think, and then Prandtl number 1/3. Okay, so this is basically directly coming out from the Reynolds analogy, but few people using it, okay, because the error from this equation is a little bit too much. It's overshoot, okay, the value based on this correlation is a little bit higher than the reality, okay. So a more common Nusselt number equation people use, again, this is for iso heat flux condition. Okay, most of the equation provided is for iso heat flux for the pipe flow. It's more realistic, okay? So the Nusselt number, so in that sense, the Nusselt number is basically the same, all right, for inside the pipe. So I don't have to put a bar on top of it. It's the same along the pipe. So the Nusselt number D, but we can say Nusselt number D, right? D, that doesn't matter. It's just tell you that's for the diameter, that's for the pipe flow, okay? 0.023 times Reynolds number 0.8, Prandtl number 0.4. That's a better correlation, but still there's a limitation, okay? So now if we move on to chapter 6, it gives you a better equation than this, okay? So that equation looks like this. So now we can consider this is the heating, okay? For the power of 0.4 on the Prandtl number, that indicates it's the heating from the pipe to the fluid, okay? So we can replace this 0.4 by let's say N. So if N equals 0.4, that's for heating. Okay, but how about cooling? That's some application you want to cool the fluid, right? Okay, then N equals to 0.3. That indicates it's cooling. Okay, so this is a often used equation. Okay, I put the star here. Okay, so that's much more popular than the previous equation. Okay, it's more accurate. Okay, but still. There's some limitation for this. This has to be a mid-range Prandtl number. So there's a requirement, limitation for this. So the Prandtl number requirement is from 0.6 to, I think it's 100, right? Yeah, exactly. Median range, it's not median range. Actually, it covers a wider range already, okay? So for this equation, okay? To be used. Make sure your Prandtl number. Usually gas is what? Air is 0.7, water is what? 2, 3, okay, Prandtl number. So it's within the range, okay. So that's a good equation to take. But if you really want a wider Prandtl number or Reynolds number range, okay, there's another equation, 6.4b, okay, which is a little bit better, even better equation, okay. So let me write it to you. Nusselt number equals 0.0214 times Reynolds number 0.8 minus 100 times Prandtl number 0.4. Okay, this is another equation you can use. That's for very little Prandtl number. Okay, if your Prandtl number is between 0.5 to 1.5. Okay, look at the range. 0.6 to 100 is a bit much wider than this, right? If you have a small range Prandtl number, okay, very tiny. Basically, this is basically in the gas or air range, right?
Dr. Zhang.
Yes.
Does the like the last equation, does the N change on the PR, or is it just always 0.4?
Which equation? That's that equation for the small Prandtl number?
Yes, sir.
It's just 0.4. It didn't say that actually heating and cooling. It should be the same. Okay. It's not 0.3. Okay. It didn't indicate it. It didn't use the n. Okay. In that sense, this is a totally different equation. So that works for both heating and cooling. Okay. So as you know, those equations, they all has limitations. For heating, cooling, there's some difference on the Nusselt number, but if the equation already have 10%, 15% error, 2% difference between heating, cooling, that's negligible. So in that sense, some of the practical application, they don't separate it. Okay. So this is the Prandtl number, small Prandtl number, and also there's the Reynolds number range, 10 to the 4 to 10 to the 6. Okay. So that this equation has a pair, right? And also a Nusselt number equals for a larger Prandtl number. Okay. So this equation for the median size Prandtl number. Okay. This is for small. Then this one is for actually very large Prandtl number. You can extend it to 500. Okay. So equation looks like this: 0.012. Okay, Reynolds number to the power of 0.87 minus 280 times Prandtl number to the power of 0.4. Okay, so that's for the Prandtl number between 1.5 to 500. Okay, now if you reach to 500, you probably cover the most of the material on Earth you use commonly. Okay, and for the Reynolds number, this is also has a wider Reynolds number range. I think it's wider, right? Yes, 3,000 to 10 to the 6. Okay, so these are those experimental correlations. You know, they have a range of Reynolds number that tells you basically they test this range. It looks okay. If you're outside this range, then it's getting crazy. So you better follow this, you know, limitations. Okay, be careful. So this heat transfer now become a very practical science. Okay, very practical engineering subjects. Okay, it's all about picking the right equation to do your calculation. Okay. So these are the most of the questions. Let me see. I think there's one more question I want to give it to you. Okay.
So Dr. Zhang.
Yeah.
When would you ever use that medium size equation?
Of course.
Since the parameters
you
can fit the small to large. Yeah,
it's up to you. You can actually have a choice. Okay. See, for the if your Prandtl number is 10, okay. Oh, you can use this. It doesn't matter. It's from a different group of researchers. They do the similar experiment. They get the different correlations. You know, different values. Okay, those equations. So if the Prandtl number is 10, you can use this equation. You can also use this equation because it falls in both equations Prandtl number range. So it's okay. Okay. Some equation coming out from 1980s. Some equation may be coming out from 2000s. Okay. Both valid for certain, you know, range. One may be a little bit more accurate than the others. Okay, these are all experimental correlations. Okay, so they determine experimentally different group, maybe at different times they determine those equations. The equation there that can be used. Okay, all has errors. Okay, maybe for your case, one equation is better than the other. Maybe they are similar. Okay, so that's your choice. Basically, it's very practical. You have a good question. You actually ask a good question. Which equation to use? Okay, then you can also check your Reynolds number. For example, if your Reynolds number is 2,000, maybe you take the first one, the median size one. Okay, because well, it didn't say. But it seems like you have less restricted Reynolds number restriction. Okay, so that's the process. Did I answer your question?
Yeah, thank you.
Yeah, you're welcome. Okay, it's okay. You have many choices right now. So right now, I'm not presenting you just one equation to use for all your application. No, I present you maybe 10 equations, okay, for the same purpose, Nusselt number. Okay, so you pick for your best interests. Okay, so best fit for your situation. Okay, so that's now I give you one more equation, even better equation. Okay, so this equation so far for the Nusselt number, it doesn't consider the property differences. You know, in the fluid, the property near the wall. For example, the wall is heated. Okay, if the pipe is heated, the fluid property near the wall may be different comparing to the fluid property in the middle of the pipe, which is cooler. Okay, some of the property change with temperature significantly. Okay, so if you want to consider the temperature difference on the properties, okay, so then there's the equation 6.5. Okay, Nusselt number equals 0.027. Reynolds number 0.8. It's similar, looks like to me. Prandtl number 1/3. Then viscosity over viscosity of wall. Okay, see the property difference here. Okay, if the property is the same, then it's just 1 in here. Okay, if the property differs, okay, so they're taking into account the property difference. Mu means viscosity at the flow temperature. Okay, bulk temperature of the fluid, maybe the average inlet and outlet is fluid temperature, right? Then the viscosity at the wall temperature, okay, in the denominator. So that takes into account sometimes the viscosity changes a lot inside the pipe. Okay. Oh, there's one more equation. Yeah, I think that's that. The other equation is okay. Now, if you have any question, just jump in. I probably want to move to the next page. The other equation I use is for the short pipe. Okay, so these equations are the previous page. Okay, on this page, that's why I put it on this page, and then another equation on the next page. Okay, these equations are all for the fully developed pipe flow. Okay, we don't consider the entrance. Okay, you know the entrance, the portion of the front part of the pipe, the flow is different. Heat transfer is different. But comparing to a mile of pipe, maybe that 50 centimeter maybe doesn't matter that much. Okay. Okay. So in most of the situation, if you assume it's most of the pipe is fully developed, you don't have to consider the entrance region. Okay, you don't have to. So these equations are perfect. But if the pipe is really not that long, okay, you're dealing with a short pipe, okay? So let's say for the pipe L over D greater than 10 and less than 400, okay? If it's greater than 10, less than 400, okay? So basically L is the length of the pipe, D is the diameter, right? So 10 to 400, that's the ratio. In that range, you have an equation. I don't exactly know how long the entrance region, okay? That depend on the situation, depend on the Reynolds number, depend on everything, okay? But 10 doesn't mean, hey, that's only entrance region is 10. No, it could be shorter, even shorter, because that equation works for even the pipe shorter than the entrance length, okay? So that can work on 400, up to 400, so it could be much longer than the entrance length, right? So it's equals 0.036 times Reynolds number 0.8. Seems like a Reynolds number to the power of 0.8 and the Prandtl number to the power of 1/3 is a pretty accepted coefficients, power, right? So for most of the heat transfer Nusselt number relations, okay. But we're just adding stuff, right? Adding some effect from the entrance, D over L to the power of 0.055. Okay, so that's the equation.
Okay, and I think you said this is all for turbulent pipe flow, correct?
Today everything is turbulent pipe flow. We're done with the laminar. Okay.
Yeah, okay, that's what I thought. Yeah.
Okay.
Because if it's laminar, it would
Laminar,
just be a
you use that
number.
Grant's number, right? For that table,
okay.
use that plot to find the value. So here, turbulent. Okay. Remember that plot we used last time. That's only for the laminar flow. Okay.
So is this equation for the short pipe? Your L over D, that's for the whole length of the pipe, the entrance and everything. And then
yeah, of course. We're looking at
over 400, you use all the other equations.
Yeah, if it's over 400, just use other equations. But if it's like 300 or 200, maybe the other equation works too. You have a choice to make. Okay, if you feel your pipeline is fully developed, depending on how long the entrance region. Okay, sometimes you probably want to try and error and do some measurement to verify. Okay, it's not a certain answer which equation is the best. It depends on your actual situation. You see my point? So if it's 300, how do you think it's maybe works better with the other equation? Maybe my entrance length is shorter than some other pipe. Okay, so on my other pipe, maybe let's say maybe it's 50, half meter is entrance length. My pipe situation maybe 10 centimeter is entrance length. Then I don't have to follow the 400. Maybe 300 is already way fully developed. Okay, I maybe try other equation. Maybe it's better. Okay, but you can also try this equation because it didn't actually tell you what is the entrance length. So this equation maybe works for L over D equals 300. So it's not really a definite answer which equation is the best for your situation. You have to decide. That's why we need an engineer for this topic. Okay, based on your experience. You talk to the people in industry, people values experience. These are the places experience take place. Okay, does that make sense? Did I answer your question?
Yes, sir. Thank you.
You're welcome. Okay. Okay, this is for the short pipe. Okay, and the last equation. Last equation is the best. Okay, the best equation include a lot of the informations. Okay, so notice all the equations so far we have. It's all for the smooth pipes. It didn't take into account anything about the friction, but actually it did, right? In the beginning here, this is the correlation stuff from the Reynolds analogy. It's kind of like a little bit of the friction information included with a coefficient, basically. Okay, so but it will be a better equation, right? Equation 6.7 to include the frictional factors as well as the temperature property differences. Okay, so it's a little bit longer equation. 6.7. I think that's the best equation I can use, but it's the longest. It's not easy to apply. You either make a mistake in the calculation, right? But I feel that serves a better purpose. But again, still, it depends on your situation. But at least directly take into account that friction coefficient. Okay, so if you have a rough pipe, not smooth pipe, okay, you can actually calculate heat transfer, taking into account this surface roughness in there. Okay, 1.07 plus 12.7. Okay, F over 8 to the power of half. Pointer number 2/3 minus 1. Then taking into account the viscosity differences with different temperature to the power of n. Okay. Okay. And this equation is actually so many purposes for the n, different n's. Let's say n equals to 0.11 for heating, for T wall greater than T fluid. Let's say bulk temperature of the fluid. Okay. So for n equals to 0.25 for cooling. Okay, so for n equal to 0, for iso, but the problem here is, okay, yeah, I need to give you, it should be an average. Okay, this equation with these two are isothermal. You have a constant temperature. You see, you have T-wall to compare. So you need to know what is the wall temperature, right? Okay, so it's isothermal equation. Okay, but it also takes into account iso heat flux. If you don't know the surface temperature, you just put n equal to 0. Okay, so in this correlation, so basically this term is gone, and then this is also for the Nusselt number for iso heat flux condition. So this equation is good. It can consider not only isothermal and iso heat flux. All the equation here we talked about here, including the short pipe, these are for the iso heat flux equations. But this equation now, I think I like this equation the best, although it's longer. Okay. But it considers the iso heat flux and isothermal. Okay. Yes.
Next to that Preno's number, is that -1?
Yeah, -1.
Okay.
It's equation 6.7 in the textbook. My writing is bad. I know. I'm writing. My screen is vertical. I have to write like this. It's a little bit difficult for me to write. But yeah, it referred to the equation 6.7 in the textbook. Okay. So I guess that's probably the more, how to say, almighty equation. Maybe. Okay. So it has the friction coefficient. Okay, inside this. Okay, so you see that actually the whole picture, heat transfer is really related to the flow. Okay, Reynolds number, friction coefficient, those things are really from the flow, right? So let's look at an example.
So this last equation,
yep.
Would you, like, if you have enough information to use this one, is that what you would go to?
Yeah,
first?
I probably will go to, okay, this equation, especially when the strength of this equation is to do with the friction effect.
Okay. So if you have something really rough, it would be a good idea.
Really rough, you go to this one.
Or something.
But for the non-rough pipes, it might not be more accurate than the other ones. Okay, so each equation has its own strengths.
Yeah, okay. And so if it's isothermal, though, this is our only isothermal.
Yeah, isothermal, this is the only equation, I think, from textbooks. There must be some other equation, but in the textbook, this is only one. So
okay. I'm just trying to, so I don't have to think about it. I just want to be able to.
Yeah, that's a good,
you have to think about it, but
process. In a problem like this, you have to think like what you did. Okay, which equation? What's the strength or the weakness of those equations? Okay. Okay, example 6.5, okay, 6.5. Okay, so it's a 2 centimeter diameter, okay. D is 2 centimeter. Tube having a relative roughness, okay, K over D. It obviously tell me this is a rough pipe, right? You have the equation already decided to use, okay? Is maintained at a constant wall temperature. Oh, okay, it's even constant wall temperature. So it's isothermal, you have no choice but that equation, okay? Okay, and we enter the tube at 40 degrees. So T in, 40 degrees Celsius. T out is 60 degrees. Okay, it's a heating process, right? That makes sense. Okay, wall is heated, 90 degrees. So the fluid is cold, 40 degrees. Then at the end of the fluid, it becomes 60 degrees. So if the velocity of the pipe is 3 meters per second, okay, calculate the length of the tube necessary to accomplish this heating. Oh, length, how do I calculate the length? Okay. So it's not only the Nusselt number, right? You decide Nusselt number doesn't help much yet, right? You have to find so what is the thought process to finding the length? Okay, length. What length is included? Which quantity include the length in your calculation? So I would like to write down, right? So heat transfer, right? Total heat transfer from the pipe, okay? HA, okay? T out minus, no, I'm sorry. It's T wall minus T, let's say fluid. Okay, so this is our fundamental equation. H, I know I'm going to calculate from Nusselt number. Okay, where is the L at? Where is L at?
In area.
In the area. Okay, so area is surface area. Okay, this is the heat transfer from the wall to the fluid. So the entire pipe wall. Okay, that area. Sometimes people confuse about the area. Okay, be careful. So it's pi times d times L. Okay, so the A is taken care of. That's good. I like it because my L is in the A. Okay, it's good. So I need to find everything else in this equation, right? That the way we solve the problem. Okay, and my L is there, pi d is given, so it's there. So let's look at the other quantities. Do I know T wall? It's an isothermal condition, so 90 degree. Okay, is that right? Everybody follow me? What is the fluid temperature? Well, you have inlet and outlet. I think it's pretty safe to use the average of the inlet and the outlet. They're the fluid temperature. So let's say 50 degrees C. Okay. So that's the average bulk temperature, right? So we're taking care of this. Okay, anything, any unsure, just jump in. Okay. Okay, now two to go, right? We have everything here. L, pi, and the D is, of course, we all know, right? We know T wall, we know the average fluid temperature, 50 degree. Okay, so do I know H? Oh, okay, H is von Nusselt number. Isothermal condition, average Nusselt number times K divided by D. Okay, right? Is that right? Everybody follow me? Okay, so K, we should be able to get from the property. D, we should be able to be already given. Okay, so properties. Now, since we reach properties, what temperature we use to find the property? We use the temperature between the wall and you can't use 50, but the 50 is not as good as if you use average, because the surface is pretty hot. Okay, so how about average between wall and your fluid? 50 degree is like average fluid temperature, but near the wall, okay, let's say still say fume temperature. Although we don't use fume temperature much in the pipe flow. Okay, I think that would be better since you are given a wall temperature. Isothermal condition, it's good to have a surface temperature, so we can use this to estimate the property. Okay, so we use 70 degree, 90, 50, 140. Okay, if you don't have a wall temperature, if it's isothermal condition, it's good to have a first try with 50 degree. It's okay. Then it's a iteration. The next time when you calculate the average wall temperature for the isothermal condition, then you can reevaluate your property again to see if it's good enough. Okay, but the advantage of the isothermal condition is you know the wall temperature, you don't need the iteration for the properties. Okay, so based on that, you should be able to find a K. You should be able to find the viscosity. You probably need the Reynolds number, right, later. And you can find the Prandtl number. You have a density. All the property can be found from 70. So most of the isothermal, isotemperature condition problem, you don't need the iteration for the property. But for the isoheat flux, maybe you need, right? That's why I ask you to do a Excel project, right? So Nusselt number, of course, there's only one equation for Nusselt number here, okay? So Nusselt number, you have So in that sense, it's difficult to get the Nusselt number. What do you want? You need to find the Reynolds number. Prandtl number you can find easily. What is F? Okay. How do you find the F? Still remember?
You have to use that chart.
It's called Moody diagram. Remember the names. Okay, not that chart. Moody diagram. That's famous in fluid heat transfer area. You need to remember the name. Okay. You use Moody diagram to find the F. Okay. So F from Moody diagram. What do you need? Do you still remember what do you need to find F in Moody diagram? You need two numbers, right? One is Reynolds number. What is the other one?
Relative roughness.
That's right. Okay. This is given. Reynolds number, we can calculate it based on the velocity, density, viscosity we find. Reynolds number is 146,700. Pretty big, right? It's fully turbulent. Okay. So there you should be able to find your F easily. Okay. Viscosity. You have a temperature viscosity, right? So one is from the bulk temperature from 50 degree. One is from the wall temperature, 90 degree. Okay. So these two viscosity you need here, right? So what is N? This is isothermal. Okay. It is a heating. So the N is 0.11. Okay. So based on this equation, you should be able to easily find the Nusselt number, which is, do I have it? 666.8. Okay. So then you should be able to find H. Okay. So H is done. I need another page. One more left. What's left?
Q.
Q. How do you get Q?
Mass flow rate times CP times delta T of the water.
So which delta T you're talking about?
The outlet minus the inlet.
So it's 60 minus 40. It's energy increase. Okay. That's the same of the energy transferred through here. So I don't think you have any problem. You can find the CP. M dot is rho VA. Okay. Now be careful. This is the cross-sectional area. When you're looking for calculating the mass flow rate, you have to use the cross-sectional area. Okay, cross-sectional area. So it is, A is what? Here is quarter pi d squared. Okay. So the Q is 77.812 watt. So when you substitute this Q back to this equation, you should be able to find the L. Okay, L is 1.4 meter. Okay. Any questions to here? I have 10 minutes.
I have a question.
Yep.
So on the, whenever you have to find the Nusselt number, you have to find the, let me go back and look at it. You have to find the viscosity at the
bulk temperature, basically is average fluid temperature. That's why I said viscosity at 50 degree. That's your average temperature.
So we have to find three different viscosities. The one at our fume temperature, well, not fume, but you know what I mean. The bulk temperature and the wall temperature.
Yeah, I think so. There are three viscosity to be used. Fume temperature is to use to calculate the Reynolds number. Okay, Reynolds number, that viscosity is not the wall viscosity, not the average fluid temperature viscosity, it's the fume temperature, right? Okay, then viscosity, that fume temperature is used to find the rest of the properties. But for this viscosity ratio, it's the average flow temperature over the wall temperature. So that's why these two are separate. Okay. Now, let me give you a quiz in addition to this problem. Okay. Let me change the problem now. Okay. So now it's not a isothermal. It becomes iso heat flux condition. It's exactly the same problem. The length, it is 1.4 meter, okay? So my goal is to calculate the water temperature. Okay, this is the quiz problem, okay? We have 20 minutes. Let's extend it to 12 o'clock, okay, for you to submit. Okay, so I give you hints, okay? Don't worry, just take out the paper, turn on the video. Okay, let's start the quiz now. So how do you calculate water temperature? Which equation you want to use? Right? That's still the equation, right? So iso heat flux, you have an H. You should be determining the H easily. Area, right? So average T wall minus the average fluid temperature is 50 degrees, right? Is that right? Average wall and average fluid. So that's the different temperature differences you are talking about, overall heat transfer. Is that right? Okay, so that's the equation you start with. So this equation, TW is there, right? You need to just find out everything else. A, same, right? So your goal is basically, what is H? Okay. And the Q is also the same, right? Is the Q same? But let me warn you this. This one need a iteration. Because you don't have the water temperature, you don't have the fume temperature to start with to get the property. Okay, so you only have two temperatures now. So you start with 50 degrees to find the property. Okay, then you'll be able to find out a average water temperature. Then use this average water temperature you calculated to find out the property again. Then find out the second round of water temperature. Okay, this is a good practice for a very practical problem. Okay, so that's the process you're gonna go through, because now in the iso heat flux condition, you don't have a water temperature, you don't have the fume temperature to estimate the property. So what you have is only the average fluid temperature, which is 50 degrees. Use that to get property for the first round to find out your TW. Okay, so the equation, still use the same equation. Let's just do this, right? So for iso heat flux, your N is 0. Okay, are you looking at my screen? Your N is 0. So you don't have a ratio for the viscosity. So it's much easier. Okay, you just need one temperature to estimate the property, but that temperature has to be iterated to the second round. Okay, so let's practice this. Okay, let me open the submission site on Moodle. Please submit to Moodle. Okay, I'll give you time to maybe a little bit more than 12 if you want to. Okay, I just want you to spend time. I'll give you more time. Okay, maybe 12:05. Okay, just don't share your answer. Do it yourself. Okay, individually. Okay, just learn it. Try to practice it. Then you learn. You will learn this. Okay, this is important. Okay, let me. Do I need to? Okay, I can keep the sharing of that page.
What appendix are we using for water
Oh,
properties?
okay. Okay, let me send you the appendix. Okay, yeah, I already took a picture. I forgot to send it to you. Okay. Okay, right now. Here you go. That's in the textbook, appendix A9, table A9. Okay. Okay, I think here I want to say you use the average of T wall and the 50 of the fluid, right? Okay, so you have a new wall temperature calculate the first round, then use the film temperature between wall and the 50. Okay, then get a property. I think that should be, second round should be accurate enough. Be careful, the second round, the Q is changed a little bit too, because there's a CP there, right? You have a different temperature, your CP will be different, a little bit different, okay?
And I'm assuming on this chart that this times 10 to the negative fourth just carries down all the way on all these numbers for viscosity.
What's your question again? On which chart?
For the properties of water.
Uh-huh.
So like at 70 degrees Fahrenheit, you got like 9.8 times 10 to the negative fourth. For viscosity, I'm assuming that number came down all the way.
You mean, I think the here is Fahrenheit, but here this problem is Celsius. So you use the Celsius. You don't exactly have that 50, for example, Celsius. So probably you need to do a little bit of interpolation between the two values surrounding it. So
well, I did.
That's the first try. Then you get the temperature. Based on the first property, you should be able to calculate the water temperature, right? So now you have a better water temperature now. You have a water temperature, then you can find out your film temperature between water and the average fluid temperature, okay? So use that temperature to find the property again, okay?
Well, what I'm saying is, so I did that, and I'm just using an example for like the column. If you look at the column or the row for 1.11 degrees Celsius, your viscosity is 9.8 times 10 to the negative fourth. And then the one right below that is 8.6. I'm assuming that's 8.6 times 10 to the negative fourth. So why would there be that big of a change?
Yeah, it's
just
10 to the negative 4, of course. Yeah.
So that's what I was thinking.
Yeah. Okay, it's 10 to the negative 3 for the first 1, 2, 3, 4 data. Then after that, it's 10 to the negative 4. Then it's negative 5.
Yes. That's what it has to be. I just wanted to make sure.
Okay.
Dr. Zhang.
Yeah.
Are we taking the length of the pipe to be 1.4 meters?
Yeah, I wrote it here, 1.4 meter. Yeah.
Making sure.
Yeah, and also I write down the diameter, velocity, and the relative roughness, in case you don't have the question statement, problem statement. But actually, thanks to Kalen, she posted the question statement on our group, our class group, so it's there. That's roughness, inlet outlet temperature, diameter, and flow velocity. That's what you need. Okay, you don't have a water temperature in this problem. It's iso heat flux. Okay. One thing, be careful. This is the dynamic viscosity mu. Okay, when you calculate the Reynolds number with mu, it's rho v d divided by mu. Sometimes in other example in the book, they use nu, the kinematic viscosity. Then the equation is v times d divided by nu. Okay, here is you have to times v, times density rho v d divided by mu. Okay, that's the Reynolds number.
And when is this due, Dr. Zhang?
It should be 12:05. You have 6 more minutes. I can extend it to 12:10 if you guys want. It doesn't matter. It's just a practice. I want you to, everybody, 22 of you here know how to do this problem. Okay, that's my goal. Okay, so I'm just use it as a quiz, but Really, I want you to know how to do this problem. But right now, as of right now, the Moodle is 12:05. I think you can hope everybody can submit by then.
Are you extending it or is it still 12:05?
I extended already 12:10, but no more extension. But You got almost time.
I'm in the middle of interpolating for my second.
Okay, so yeah. Okay, let me see how many submitted. Just keep doing. I maybe give you 1 or 2 minutes. Okay. Let's submit as much as you can. Okay, it's okay. You always will have partial points. Okay, let me give you 2 more points. Last 2 minutes. 2 minutes. Okay, 2 minutes. Okay, 12. I have a class on 1 o'clock, and I need to finish it here. Okay. You still can submit, right? Even if I don't change the due time, even past the due, right now it's due 12:10. So you still should be able to submit after 12:10, right?
What's the due time, Dr. Zhang?
1 more minute. 12:12. I think it's time for you to stop writing and start to submit. To take time to submit, right? It's okay. I think I will grade based on the, the process, those values you have, and you have all partial points. The final answer maybe it's just 1 or 2 points. Oh, Jake has a question. So what's the topic for our last project? Sure, last project is chapter 6, the piping and the external body, but basically just do a tube flow, pipe flow. Laminar or turbulent. Okay, it's okay. I received a couple of you submitting me picture. Let me see. Oh, it's okay. If you really have difficulty to Moodle, you can submit through my class group. Oh no, it's just individual text to me. Yeah, in the group me. It's fine. I received 2 of you from this.
When is our next project due?
Next project will be due on Sunday next week. Okay, Sunday. Give me some time to review. I need some time, and yeah, I probably need to post the grade Wednesday the following week. So Sunday probably is the latest.
Will our other video projects be graded by the time that that's due?
Yeah, well, I'm reading, watching number 3 now. Okay, good. Let's call it for today. Okay, have a good afternoon.我鼻子里不通。